In this video, let us try to understand how to write the Verilog code for full adder in gate level modeling. So if you observe this particular slide, so I'm considering a 1-bit full adder which contains 3 inputs. So 3 inputs are nothing but A, B, Cin, and it contains 2 outputs which are nothing but sum and carry. So after this you need to write the truth table. So truth table will give the relationship between inputs and outputs. So if you observe, there are 3 inputs and 2 outputs. So if 3 inputs are there, 2 power 3 different combinations we can expect. That is 2 power 3 is nothing but 8, which will be from 0, 1, 2, 3, 4, 5, 6 and 7. So but they are in the form of decimal equivalent. Now we need to write the binary equivalent of 0, 1, so on till 7. So this is nothing but the 0 equivalent, this is 1 equivalent, 2 is nothing but 0, 1, 0, 3 is nothing but 0, 1, 1, 4 is 1, 0, 0, 5 is 1, 0, 1, 6 is 1, 1, 0, 7 is 1, 1, 1. Now let us try to perform the addition of this 3 different bits. So 0 plus 0 plus 0 will give sum 0 and carry 0. Next 0 plus 0 plus 1 will give sum 1 carry 0. Next 0 plus 1 plus 0, which is nothing but sum 1 carry 0. Next 0 plus 1 plus 1. So 0 plus 1 plus 1 is nothing but 2. 2 in terms of binary will be 1, 0. So this 1 is called as carry, this 1 is called as sum. So 1, 0. Next 0 plus 1, or else 1 plus 0 plus 0, which is nothing but sum 1 carry 0. Next again 1 plus 0 plus 1, which is nothing but 2. 2 equivalent is 1, 0. Same thing is applicable here also. 1 plus 1 plus 0 is 2, which is nothing but 1, 0. Next one is 1 plus 1 plus 1, so which is 3. 3 in terms of binary is 1, 1. So this one is called as carry, this one is called as sum. So 1 and 1. So once if you are done with writing the truth table, next we need to do the K-map of outputs called as sum and carry. So let us write the minterms for carry and sum. So for carry, sum of minterms. So consider the position where it is 1. So check the equivalent of this one, which is nothing but 0, 1, 1, which is nothing but 3. Next 1, 0, 1. 1, 0, 1 is 5. This is 6. This is 7. So 3, 5, 6 and 7. Now try to perform the K-map of this minterms for carry. So first I am doing for carry. So here inputs are nothing but A, B, Cin. So in this particular positions you need to put as 1. So 3, 5, 6 and 7. Now we have to do the grouping. So here this is one pair. So the answer for this pair is, here this 1 is for A dot, check the common bit among 0, 1 and 1, 1. So the second bit 1 is common, that is for Cin. So this is how we need to write. So A, Cin is the answer for first pair. Next this is again one pair. Now let us write the equivalent for this, which is A dot, check the common among 1, 1 and 1, 0. First bit 1 is common, which is for B. Next this one vertical pair. So the answer is nothing but 1, 1, which is B, Cin. So finally the answer that I got for carry is the summation of all these pairs, which is A dot B plus B dot Cin plus Cin dot A. So the same thing you can observe here. Carry is equal to AB plus BCin plus CinA. Now let us try to write the minterms for sum. Sum is equal to sum of minterms. Check the position where it is 1. So here the equivalent is 0, 1, 1, which is 1, 2, 4, 7. So 1, 2, 4, 7 are the minterms. So 1, 2, 4 and 7. Inputs are nothing but A, B, this is Cin. So here grouping is not possible, so everything should be written individually. So if you take the equivalent of this, this is 0 is there for A, which is nothing but A bar dot B dot Cin bar, and this is again one single. If you write the equivalent for this, it is A bar dot B bar dot Cin. Next answer for this is 1, 1, 1, which is A, B, Cin. Next this is A dot B bar dot Cin bar. So finally the answer which I got for sum is, so the answer is A bar B bar Cin, A B bar Cin, next A bar B Cin bar plus A B Cin, which is nothing but A XOR B XOR Cin. Now based upon this Boolean expressions we need to draw the logic diagram. So if you see this particular logic diagram, this is nothing but the way of implementation of full adder by using two half adders and one OR gate. So if you observe this particular module here, this module is one half adder, this module is another half adder, followed by one more OR gate. So implementation of full adder using two half adders and one OR gate.